In this video, we will complete the structural analysis of the common Fink-type truss shown here for a building that is 24 feet wide. The trusses are provided at a spacing of 2 feet on center. Our analysis will be strictly limited to the axial forces in the framing members using the method of joints and the method of sections. The structure has asphalt shingles roofing with 3-ply felt and 1/2-inch plywood. The structure will also have polystyrene insulation which is placed over a 1/2-inch gypsum board ceiling. The loads on this project are based on the requirements in the International Building Code or the IBC, which is adopted across the United States. Please see the links in the description for more information about the adoption of the IBC and to get access to a free online copy of the code. For this project, we will use the 2024 version of the IBC code. The loading requirements for buildings are provided in Chapter 16 of the IBC. For this analysis, we will consider the dead plus roof live load combination. Let us consider the dead loads on the structure. Dead load is the actual weight of all the materials of construction including fixed service equipment. Based on the roofing we have described, we can estimate the uniform dead load at the truss top chord after considering the slope will not exceed 10 pounds per square foot. This load will be applied at the top chord. Similarly, for the ceiling, we can estimate that the dead loads based on the materials that we have described will not exceed 10 pounds per square foot, which will be applied to the bottom chord. Let us now consider live loads. According to Table 1607.1 of the IBC, ordinary pitched roofs should be designed to support a uniform live load of 20 pounds per square foot. The code allows live load reduction, but we will not use it for this project. For the ceiling, Item 27 on the same table requires uninhabitable attics to be designed to support a uniform live load of 10 pounds per square foot. These are the uniform loads that we will use in our analysis. Let us define the joints or nodes. These are the points where the members connect to each other and where load is transferred or distributed to the members framed at the joint. In order to use the method of sections and method of joints, the joints are assumed to be pinned, which means that no moments will develop at the connections in our analysis. The joints are as follows: Node 1, Node 2, Node 3 at the ridge, Node 4, Node 5, Node 6 at the ceiling, and Node 7 also at the ceiling. Let us now provide the member numbers. Member 1 extends from Node 1 to Node 2. Member 2 extends from Node 2 to Node 3. Member 3 extends from Node 3 to Node 4. Member 4 extends from Node 4 to Node 5. Member 5 extends from Node 5 to Node 6. Member 6 extends from Node 6 to Node 7. Member 7 extends from Node 7 to Node 1. Member 8 extends from Node 2 to Node 7. Member 9 extends from Node 7 to Node 3. Member 10 extends from Node 3 to Node 6. Member 11 extends from Node 6 to Node 4. The eaves members will not have axial load, but we will consider the vertical load they are supporting as acting on Node 1 and Node 5. Let us now specify the dimensions. We will start with the projected horizontal distances. The eaves are 1.5 feet wide or 1 foot and 6 inches wide. The distance between Node 1 and Node 5 is 24 feet. The horizontal distance between Node 1 and Node 2 is 5 feet. And 3 feet between Node 2 and Node 7. And 4 feet between Node 7 and Node 3. And 4 feet between Node 3 and Node 6. And 3 feet between Node 6 and Node 4. And 5 feet between Node 4 and Node 5. The vertical distances are as follows. The vertical distance between Node 1 and Node 3 is 5 feet. The vertical distance between Node 1 and Node 2 is 2 feet and 1 inch. The vertical distance between Node 2 and Node 3 is 2 feet and 11 inches. A copy of the PDF file showing the truss schematic including dimensions, nodes and member numbers is provided in the description. Please download for your reference. As we have noted, the trusses are spaced at 2 feet on center and are supporting uniform load. Members supporting uniform loads along their length will be subjected to both bending and shear forces. This means that the top chord and bottom chord members will also be subject to bending and shear and must be designed against these loads. As we noted at the beginning, the scope of this example only includes axial loads. Therefore, we will strictly focus on the determination of axial loads at this time. In order to use the method of joints and the method of sections, we will first need to resolve the uniform loads that we have determined into joint loads. Each node will support loading based on its tributary length. Let us start with node 1 and node 5, which will have the same load due to truss symmetry. The loading from the top chord supported at node 1 may be determined as follows. First, the tributary width will be equal to 1.5 feet at the eaves plus 2.5 feet, which is halfway between node N1 and node 2. This is 4 feet of tributary length. The next step is to multiply this length by the 2 feet tributary width, which is the truss spacing. And then we multiply by 30 pounds per square foot, which is the total uniform load at the top chord. The total load is 240 pounds, which is the direct load coming from the top chord. We also need to consider the load coming in from the bottom chord. The tributary length will be half of 8 feet, which is halfway between node N1 and node 7. Therefore, the tributary length is 4 feet. We then multiply this by the 2 feet truss spacing. And then we multiply by 20 pounds per square foot, which is the total uniform load at the ceiling. The total load is 160 pounds. This is the ceiling load that is coming through the bottom chord to the support. The total direct force that is coming to node 1 is therefore 240 pounds plus 160 pounds, which is 400 pounds total. Due to symmetry, the same conditions are present at node 5, and therefore we will apply the same load to node 5. We will determine the loading at node 2 and node 4 using the same process. The top chord tributary length is 6 feet and the tributary width is 2 feet since the trusses are spaced at 2 feet on center. The loading is 6 feet times 2 feet times 30 pounds per square foot, which is 360 pounds. Let us consider node 6 and node 7. The bottom chord tributary length is 8 feet and the tributary width is 2 feet since the trusses are spaced at 2 feet on center. The loading is 8 feet times 2 feet times 20 pounds per square foot, which is 320 pounds. Finally, let us consider node 3. The top chord tributary length is 7 feet and the tributary width is 2 feet since the trusses are spaced at 2 feet on center. The loading is 7 feet times 2 feet times 30 pounds per square foot, which is 420 pounds. These are the nodal forces that we will use in our analysis. Before commencing with the determination of reactions and the evaluation of member forces, let us discuss the boundary conditions. Boundary conditions in structural analysis refer to the type of supports that are provided to a structure or system. By defining boundary conditions, we are defining whether the support is vertical only, both vertical and horizontal, or if the support also constrains rotation. The type and magnitude of member forces are influenced by the boundary conditions provided for a system. First, we will look at it from a design perspective. Boundary conditions are dictated by the design intent of the designer and the ability of the supporting system to provide the required support. In other words, we cannot say we are constraining against rotation when the connections or supporting system does not have the capacity to offer such constraints. For this truss, we only need vertical support, which means that the wall supporting the truss must have sufficient capacity to support the vertical reactions. Since we do not need to constrain the truss against rotation at the supports, we will not provide any fixity against moments. Therefore, the truss will not transfer any moments or moment couple to the wall. We will therefore use pinned connections. A pinned connection cannot transfer moments but will transfer vertical forces and lateral forces. Let us talk about lateral forces and the lateral restraint that a pinned connection provides. Suppose we take the same truss and remove the web members and the bottom cord. Please note that the connection at the top is still a pin connection. If a force is applied at the top, the truss members will be under axial compression. Consequently, the supports will experience a force vector which can be resolved into a horizontal thrust outwards and a vertical force downwards. In this type of a system, we do not have a choice but to provide pinned connections that can resist both the vertical force and outward thrust. What if we bring back the bottom cord? Assuming that the top cord is adequately connected to the bottom cord, we can see that now we have the option to transfer all the outward thrust force at the base of the top cord into the bottom cord so that the bottom cord is in tension. To ensure that this happens, we need to release at least one of the pinned connections laterally so that no reactions will develop. In structural analysis, this is done by using a roller support. A roller support can provide vertical support but cannot provide lateral support, which means that no lateral reactions will develop. By doing this, all the lateral force will be resisted by the bottom cord. This is what we shall do to the truss system. We will replace one of the pinned supports with a roller support. From a practical perspective, we do not want to transfer the outward thrust forces to the wall because the wood-framed wall does not have the capacity to support lateral out-of-plane loads acting at the top of the wall. As we have said, to prevent the development of lateral reactions in our analysis, we will replace one of the pinned supports with a roller support that is free to move laterally. Such a system does not have lateral reactions. A truss designed under these boundary conditions will have maximum member axial forces, and this is what we want. From an analysis perspective, the pin and roller supports ensures that the truss is statically determinate. This means that the number of equilibrium equations available matches the number of unknown support reactions, which we have reduced to just the vertical reactions. This allows for straightforward analysis using static equilibrium alone, without requiring advanced analysis methods. We will use static equilibrium methods such as the method of joints and method of sections. The next step is to calculate the reactions. The system is statically determinate, and we can calculate the reaction using equilibrium equations. For a system in static equilibrium, the vector sum of all external forces acting on the system must be zero. Since we are considering vertical forces only, all vertical forces must add up to zero. This means that since all forces are acting vertically downwards, the reactions will be acting vertically upwards and their sum must be equal to the total force acting downwards. Since the truss is symmetric about the center line, the reaction at node 5 will be equal to the reaction at node 1. Therefore, the reactions may be determined by adding all the forces and dividing by 2. All the forces will add up to 2,580 pounds. And the vertical reaction at each support is 2,580 divided by 2, which is 1,290 pounds. Therefore, each support must have adequate capacity to support 1,290 pounds. We have said that the system is in static equilibrium, and we can therefore use static equilibrium equations. In this case, static equilibrium means that the truss is completely at rest, it is not in motion or unstable due to any net unbalanced force or net unbalanced moment. Therefore, for a two-dimensional system, the sum of all forces in the y direction is 0 and the sum of all forces in the x direction is 0. Similarly, the sum of all moments about any point is 0. In order to easily analyze the truss members using these equilibrium equations, every force vector whose direction is at an angle to the horizontal axis will need to be decomposed into the vertical and horizontal components. Therefore, The horizontal component is the product of the force and the cosine of the angle between the force and the horizontal axis. On the other hand, the vertical component is the product of the force and the sine of the angle between the force and the horizontal axis. Let us now discuss some rules to help us proceed with consistency. We will apply the following sign convention. All force vectors in the upward direction will be positive forces, which means that forces in the opposite direction will be negative forces. All force vectors pointing towards the right side direction will be positive forces, which means that forces in the opposite direction will be negative forces. Finally, all counterclockwise moments will be positive moments, which means that all clockwise moments will be negative moments. These rules will help us proceed with consistency when adding forces and moments. In this analysis, we are dealing with two types of forces. There are external forces that are applied to the system and internal forces that are developed in each member. The purpose of our analysis is to determine the internal forces given the external forces. Before proceeding, we need to understand the conventions for representing internal forces. If you take a piece of 2x2 wood between your hands and start pushing into the wood, you will experience a concurrent force acting within the wood and pushing outwards on your palms. The force you are applying is a compressive force, and the force that you are experiencing from the wood is the reaction, which is represented by the two arrows pointing outwards. Therefore, compressive force is represented by two opposite arrows pointing outwards along the longitudinal axis of a member. Similarly, if you pull a spring so that it is in tension, the spring will be pulling on your hands inwards so that it wants to go back to its original state. Therefore, for a member in tension, the internal forces are represented by two opposite-facing arrows pointing inwards into the member. These conventions are critical to a successful analysis of the member forces and will therefore be applied in our analysis. Let us start with node 1 and draw a free body diagram of the forces acting at node 1. First, we have the 400-pound force, which is the sum of the roof and ceiling load that is acting directly at node 1. Then we have the reaction, which we determine to be 1,290 pounds. Then we have the axial force at member 1 and the axial force at member 7, which are the unknown forces that we need to determine. We will assume that these are tensile forces, which we have just said is represented by the arrow pointing into the member. For all joints where internal member forces are unknown, we will first assume that the forces are tensile forces. Our assumption will be verified by the sign on the final answer. If the member force is positive, then the force is indeed a tensile force. However, if the member force is negative, then the force is a compressive force. The axial force at member 1 is inclined at an angle to the horizontal. We will call this angle theta. We need to decompose this to the horizontal and vertical components as we discussed. Based on the truss dimensions and using trigonometry, we can determine that the angle is 22.62 degrees. The horizontal component is the product of F1 and the cosine of the angle, while the vertical component is the product of F1 and the sine of the angle. Let us now consider the equilibrium equations. The sum of forces in the y direction is 0. Keeping in mind our sign convention, we have 1290 plus negative 400 plus F1 sine theta equals 0. 1290 minus 400 is 890. So we have 890 plus F1 sine theta equal to 0, or F1 sine theta equal to negative 890. Theta is 22.62, and therefore F1 is the quotient of negative 890 and the sine of 22.62 degrees. Therefore, F1 is equal to negative 2,314 pounds. The negative sign reveals that F1 is a compressive force and not a tensile force as we had assumed. Therefore, member 1 has 2,314 pounds of compressive force. Since we have determined that F1 is a compressive force, we will represent it as a compressive force with the arrow pointing away from the member towards the joint. Let us now solve for F7. F7 is a purely horizontal force. We will therefore consider the equilibrium equation in the horizontal direction. All forces in the horizontal direction will add up to 0. The only forces acting at node 1 in the horizontal direction are F7 and the horizontal component of F1. We do not have a horizontal reaction because we provided a pin support on one end and roller support to the other end, thereby preventing the development of horizontal reactions. Therefore, keeping in mind our sign convention, the equilibrium equation will be F7 plus the product of negative F1 and the cosine of theta equals to 0. Note that the force component F1 cosine theta is negative based on our sign convention. Since we have already determined that F1 is 2,314 pounds and we know that theta is 22.62 degrees, the product of F1 and the cosine of theta is 2,136 pounds. Solving for F7, we determine that F7 is therefore 2,136 pounds. Since the sign is positive, F7 is a tensile force just like we assumed. We have calculated the forces at member 1 and member 7. The next member that we will evaluate is member 8. Actually, we do not even need to know the forces at member 1 and member 7 in order to determine the force at member 8. We are going to use the method of sections, which is very useful when you need to quickly determine the internal force of a particular truss member. To commence with this method, we will apply an imaginary cut along a straight line through members F2, F8 and F7. The internal member forces will now become external forces acting at the point where each member was cut. This isolated system is also in static equilibrium, and we can use this fact to determine the unknown force at member 8. Please note that the force at member 2 is also unknown, but this is not a problem as we shall see shortly. Since this system is in equilibrium and is part of a statically determinate system, we can use any of the equations of equilibrium to solve for unknown forces. The easiest way to find member 8 is to use the moment equation. Since we have multiple forces whose longitudinal axis passes through node 1, the moments due to these forces about node 1 is 0. Since the longitudinal axis of F2 passes through node 1, the moment due to F2 about node 1 is 0. The longitudinal axis of the force at member 8 does not pass through node 1, and therefore, if we take moments about node 1, we can isolate F8 and determine its magnitude. Please keep in mind that because the system is in equilibrium, all moments about node 1 must sum up to 0. The 400 pound at node 1 and the 1290 reaction at node 1 all pass through node 1, and therefore the moment arm is 0, which means that the moment due to this forces about node 1 is also 0. Additionally, the longitudinal axis of F2 and that of F7 both pass through node 1, which means that they will not develop any net moments about node 1. Therefore, we will ignore all forces that are generating no net moments about node 1. We are left with the 360 force at node 2 and F8. F8 is inclined at the angle beta to the vertical axis. Using the dimensions provided and trigonometric relationships, we can determine that beta is 55.23 degrees. We will decompose F8 into a horizontal component and a vertical component. The horizontal component is the product of F8 and the sine beta, and the vertical component is the product of F8 and the cosine of beta. We will use these components to calculate the moment. A moment is the product of a force and the perpendicular distance between the force and the turning point. By decomposing F8 into a vertical and horizontal component, we can easily determine the perpendicular distance between each component and the turning point, which in this case is node 1. The distance between each component and node 1 will be measured from node 2 because this is where we will resolve the force into its two orthogonal components. The horizontal distance between node 1 and the vertical component of F8, which in this case is the product of F8 and the cosine of beta, is 5 feet. The vertical distance between the horizontal component of F8, which in this case is the product of F8 and the sine of beta, is 2 feet and 1 inch, or 2.083 feet. Now that we know the distances, we are ready to write the equilibrium equation. We start by stating that the sum of moments about node 1 is 0. Keeping in mind the sign convention for moments where we said that counterclockwise moments are positive, we can write the following. Negative 360 times 5 feet, plus negative F8 cosine beta times 5 feet, plus negative F8 sine beta times 2.083 feet, equal to 0. We know that beta is 55.23 degrees, so the equation becomes negative 1800 minus 2.85 F8 minus 1.71 F8 equals 0, which is minus 1800 plus minus 4.56 F8 equals to 0. Solving for F8, we get F8 is negative 395 pounds. This means that F8 is a compressive force and not tensile as was previously assumed. This is how we use the method of sections to solve for an unknown member force. Having determined F8, we can easily use the method of joints to determine the force at F2. The angle between F2 and the horizontal is similar to the angle at node 1. We will call this angle theta, just like we did when working with the similar angle at node 1. We determined that angle theta at node 1 is 22.62 degrees. Therefore, angle theta at node 2 is also 22.62 degrees. We have several forces acting at node 2. First, we have the vertical external force, which is 360 pounds. Then we have F1, which we determined was a compressive force and therefore shown pointing towards the joint. We have already determined that the magnitude of this compressive force is 2,314 pounds. We also have F8, which we have just determined to be a compressive force of 395 pounds. The force is compressive and therefore shown pointing outwards towards the joint. We do not know force F2 at member 2, and this is the force we are trying to determine. Since we do not know F2, we will assume that it is a tensile force like we have done previously and will therefore represent it by an arrow pointing away from the joint and into the member. All the forces at this joint are inclined at an angle to the horizontal or vertical axis. Therefore, we need to break down the forces into the vertical and horizontal force components. Starting with F1, we have F1 sine theta and F1 cosine theta. For F8, we have F8 cosine beta and F8 sine beta. F2 will have F2 sine theta and F2 cosine theta. These are the force components that we need to work with. Since the joint is in equilibrium, the sum of horizontal forces or horizontal force components acting at node 2 is 0. Keeping in mind the sign convention, the sum of horizontal forces acting at node 2 is F1 cosine theta plus F2 cosine theta plus negative F8 sine beta equals 0. We know that theta is 22.62 degrees and beta is 55.23 degrees. The equation becomes 2,314 times 0.923 plus F2 times 0.923 minus the product of 395 and 0.821 equals 0, which eventually reduces to 1811 plus 0.923 F2 equals 0. Solving for F2, we determine that F2 is negative 1,963 pounds, which means that it is a compressive force. Therefore, the force at F2 is a compressive force of 1,963 pounds. Another member whose force we can easily determine without relying on any knowledge of other member forces is the force at member 6. We will use the method of sections to determine this force. This member is already oriented in the horizontal direction, which means that we do not need to decompose it. This will make our work very easy. To commence with this method, we will apply an imaginary cut through node 3 and vertically down to member 6. This will essentially split the truss into two parts. The internal member force at member 6 will now become an external force acting on the half truss at the point where the cut was made. This isolated half truss system is also in static equilibrium, and we can use this fact to determine the unknown force at member 6. We will take moments about node 3. But before proceeding, let us look at all the forces and their distances to make sure we have everything that we need. The 320-pound force at node 7 is 4 feet from node 3. This is the perpendicular distance between the force and node 3. In other words, since this is a vertical force, we want the horizontal distance from the force to node 3, which is 4 feet. Similarly, the horizontal distance between node 3 and the 360-pound force at node 2 and node is 7 feet. The horizontal distance between node 3 and the 400-pound force at node 1 is 5 feet plus 7 feet, which is 12 feet. This is the same distance for the 1290-pound reaction at node 1. F6 is a horizontal force. We are interested in the vertical distance between the force and node 3. In this case, the distance is 5 feet. We will start by stating that the sum of moments about node 3 is 0. Keeping in mind the sign convention for moments, we can write the following. 320 times 4 feet, plus 360 times 7 feet, plus 400 times 12 feet, plus negative 1290 times 12 feet, plus F6 times 5 feet, equals 0. If we add up all the numbers and solve for F6, we come up with F6 equals 1360 pounds. This is a positive force, which means that the member is in tension just like we assumed. Therefore, member 6 has a tensile force of 1360 pounds. The next member is member 9. We need to determine the force at member 9. As usual, we will assume that this is a tensile force pointing away from the joint into the member. We will use the method of joints to solve for the force at member 9. We have the option to use either the equilibrium equation based on the sum of the vertical forces or the sum of the horizontal forces. Since there are less members with vertical components, we will use the sum of the vertical forces. We need to determine the angle between member 9 and the horizontal. We will call this angle phi. The angle is 51.34 degrees based on the dimensions of the truss. Therefore, the vertical component of F9 is the product of F9 and the sine of phi. We also need to determine the angle between F8 and the horizontal. We will call this angle alpha. The angle is 34.77 degrees based on the dimensions of the truss. We could also have used beta, which we had previously determined, but we will use alpha. Therefore, the vertical component of F8 is the product of F8 and the sine of alpha. If we had used beta, the vertical component would have been the product of F8 and the cosine of beta. The sum of vertical forces and vertical force components acting at node 7 is 0. Keeping in mind the sign convention, the sum of the vertical forces acting at node 7 is F9 sine phi, plus F8 sine alpha, plus negative 320 pounds equals 0. The only unknown in this equation is F9. We can therefore simplify and solve for F9, which is 698 pounds. This is a positive number, so the force is indeed a tensile force just like we assumed. Therefore, member 9 has 698 pounds of tensile force. In summary, we have determined that member 1 has 2,314 pounds of compression force, member 2 has 1,963 pounds of compression force, member 6 has 1,360 pounds of tensile force, member 7 has 2,136 pounds of tensile force, member 8 has 395 pounds of compression force, and member 9 has 698 pounds of compression force. Due to the truss symmetry, the internal forces at members on the right side will be equal to the forces at similar members on the left side. Therefore, these are the internal axial member forces that should be used to design the truss members and connections. If you enjoyed this video, don't forget to give it a thumbs up and subscribe to the channel, and do not forget to hit the notification bell so you never miss an update. Your support helps us keep creating great content, and we'd love to have you join the community. Thank you for watching.